Hang in here. Don't be texting everybody how wonderful this is. Hang on a second. Hang on. Now listen. So I did a lower sum. I did an upper sum. I used inscribed rectangles. I used circumscribed rectangles. Right? I want to do one more. It's called, I call it middle scribed. So we already know. See, what's funny is I already told you the big exciting conclusion. To really do this accurate and better, do an infinite number of rectangles. But one way to do it better with just 4 rectangles is to do middle scribed instead of left scribed and right scribed or inscribed or circumscribed. All right, I need my picture again. Hang on just a second. Let me see here what I had. I had this thing at 3, going up here. This is 2. It hit right here at 7. I had these things partitioned into 1, 1/2, and 3/2. These are my 4 rectangles, right, you guys? There they are. Okay, we were topping them off at the left or the right to try to get our inscribed and circumscribed rectangles. I want to do middle scribed. So that means I'm going to go up here. I'm going to use this value. Listen, I'm not doing 2 I'm doing this 1 rectangle, but I'm picking this number to plug in and get my height. When I get this height, I'm going to top it off with a horizontal height, you know? Look what I get. I get a little over error and a little under error, all in the same rectangle. Look, it looks better over here. When I middle scribe this, I top it off and call that my rectangle. Look, a little under error, a little over error. This is pretty cool. This will be nice and accurate. Let's do 4 middle scribed rectangles. So I'm calling this the middle sum. I'm going to use what I call middle scribed. Are you with me on that? Middle scribed rectangles. All right, what's the width of each rectangle? No. What's the width of each rectangle? Because there's still 4 rectangles. The width is 1/2. The width is 1/2. But what I'm using to plug in to get the heights is this middle height or whatever. It's f of, I don't even know what to call it. I think I'll use the CI. It's not the little mi or the big mi. It's something in the middle. It's the middle actually, but I'm going to call it CI. But here I go. I want to find the middle heights. You guys understand, or did I lose you? You understand, don't you? So going to my first rectangle, I did this twice already. I found this height, that was too short. I found that height, that was too much. I want to use the middle height. So to get that middle height, I need to use this x value. What is this x value? 1/4. Thank you very much. So I'm plugging 1/4 into the function to get that height. Can y'all help me with that?
3.0625.
3.0625. You know, I don't want to round these, so I'm going to try not to round these, okay? For the second rectangle, what do you plug in to get the height? 3/4. You're right, that's a 3/4 right there.
Yeah.
Okay, I plug it in, I get this middle height, which is pretty awesome because it's a nice compromise. F of 3/4. All right, I need help again on the calculator. 3/4 squared plus 3, please help me.
3.5625.
3.5625. All right, this is cool, dude. Let's try this one. What's the next run? What's the next one?
5/4.
That is a 5/4. He's right. 1 1/4. You could call it a 1.25 if you wanted to decimalize, or a 5/4, like he said. Anybody?
4.5625.
All right. That was this guy's height. Okay. That was a middle scribed height. All right, finally the last one. 7/4 or 1 3/4 or 7/4, whatever you want to do.
6.0625.
6.0625.
Okay.
All right, those are the heights. What do I have to do now?
Multiplying by 1/2.
Oh yeah, right. Multiply each height times each width to get an area. All right, help me with that. 1.503125. Multiply this times 1/2. Did I do that right?
Yeah.
Okay.
There's no 0 there.
Oh, there's no 0 there. Sorry.
53125.
1.53125. Okay. Yeah. Okay, multiply a half times this.
78125.
All right, thank you very much. Multiply a half times this.
28125.
All right. Multiply a half times this.
3.0125.
All right, this is awesome. Dude, we found our areas. These are our areas of our 4 middle scribed rectangles. This is awesome. Now add them up, please add them up. Add them up and we'll have what we call a middle sum, which is a cool average sort of thing between that lower and upper sum. It'll be a way better estimate. It'll be a way better estimate. It still ain't exact though. It still ain't exact, but it's a hell of a better estimate. What is it?
8.60625.
60625. All right, that's my middle sum. That's awesome. Do you understand it? Are you okay? I mean, what's changing in the, I did 3 problems. I did lower sum, upper sum, and middle sum. And the only thing that changed, I guess, each time was the heights. The heights changed because the thing I plugged in to get the heights changed. I mean, the heights, the widths were always the same, but the heights changed because the x value I plugged in to get the heights changed. Right. When I used this x value, I got a certain height. When I used this x value, I got a certain height. Then I chose to use this x value, and I got a middle height. But so my heights changed in all my problems, and but this is awesome. This is awesome. All right, you ready for this? This is even more awesome. How can you get more awesome, you might ask? How can you even get more awesome, Smith? Well, it's easy for me. Awesome is my middle name. All right, you ready? This is awesome. What am I going to do? I'm going to tell you the truth. By the way, I think I just jumped to 5.4 when I tell you this, or 5.3. I'm sorry. I'm sorry, but it's the way. I'm smarter than the book. Okay, you ready? That's our best estimate so far. All right. The truth is, to find exact area, you can do this, but it's hard. This turns into this. It's not a coincidence. We just learned this Monday. We learned how to do antiderivatives. We learned how to do integrals. We use this symbol, don't we? Listen, it's not a coincidence that that symbol looks like an S. The reason it looks like an S is it kind of comes from this summation. Now listen. So here's what I'm going to do. I'm going to integrate the function with respect to x. Listen to this. Look over here. Look at that delta x. When you turn into an integral, it turns into a dx. Look at this function. That's my function. So can you connect these thoughts to that thought? I'm trying to make you see how this is a function, this is a delta x, this is a f of x, this is a dx. These are my little widths of my rectangles. These are my heights of my rectangles. And I'm adding up an infinite number of rectangles. I mean, I didn't tell you that's what that meant the other day, but now I'm saying it means this. I mean, this is one of the main uses of integration is for this area under a curve. There's other uses. It really comes down to this. They don't tell you that in 5.1, and they take you 5.2 and 5.3 and 5.4 before they finally tell you how to do it. To really get area, to really get exact area, what you have to do is called a definite integral. You didn't see this in 5.1, but I have to put bounds on this integral from A to B. I'm integrating from A to B. I'm integrating a function with respect to x, but this is the area under the curve. So let's do it. I'm erasing I want to keep that answer there, but here we go. Let's do it. I want to do this integral. What function am I integrating?
X
Duh. Thank you. X squared plus 3 is my function. I'm integrating my function. I have a dx out on the end. It's kind of like my height and my width. And then I'm going to do it. These bounds, this is a new idea. You didn't see this yesterday. This is, again, I'm kind of up in 5-4, but I don't mind telling you this. These bounds are the left and right bounds where you're going to integrate from. So what's the furthest left we are?
2.
0. And I'm going all the way to 2. I'm integrating from 0 to 2 to get the area under the curve. This is no longer, this is an infinite number of rectangles. This is going to be exact area. Here we go, from 0 to 2. All right, here we go. You ready? Whew. This is the part you learned Monday. How do you integrate? How do you integrate the x squared? Shit, you learned it Monday.
Add 1 and then we'll divide by that.
Do a reverse power rule. It's a power. It's
So it's x.
1/3 x cubed.
Yeah,
Right.
yeah, plus
Plus
3x.
3x.
And then when you integrate a 3, you get a 3x. It's an antiderivative. It's the backwards of derivatives. There it is.
Okay.
So there it is. And then what would we do Monday? We learned to put a plus c because we get this arbitrary family of functions.
Right.
Okay, hold on. When it's a definite integral with bounds, I don't put a plus c. I'm sorry. And so what I do now is I evaluate this from 0 to 2. And what that means is we plug in the 2 and we subtract plugging in the 0. Here we go. This is the exciting conclusion. When I plug in a 2, this is 8/3 plus 6 minus, you plug in the 0 and you get a couple zeros. Are you guys with me?
Yeah.
This is the answer. This is the exact area. 8/3 plus 6. That's 2 2/3. 2 2/3 plus 6. This is 8 2/3. The exact area is 8.666666666666666. That's the exact area. No error. No error. Infinite number of rectangles added up. But this is how we do it. Is this easy or what? It's easy. It's easier than adding up an infinite number of rectangles. Right. That would take you a while.
That's the exact.
You seem to be let down by the exciting conclusion. Dude, exact area under a curve? That is so beautiful. No errors. Now you can do area of curvy, crazy, curvy things. You just got to integrate them, which actually might be hard. This was an easy one to integrate, right? How do you integrate this function? Real easy. And then evaluate it.
So instead of doing all that, we could have done that.
Well, right. So I wanted to teach you about the rectangles, tell you the rectangle story. But you're right. I could have saved
No, but
45
that's
minutes
good.
if I just would have.
But no, but that's good because that's the concept.
Well, right. And it is the concept. And you have to add up some rectangles for me. So let me say something. What do I want to say? I want to say that when you're in 5-2, they practice, the homework is about adding some stuff up. And they do make you do some inscribed and circumscribed rectangles, and they do some middle scribed rectangles sort of toward the end. So there is some homework where you actually have to add up some rectangles. I would try a few of those. But like you saw today, you saw me do it. It's a little tedious. It takes a little while. It takes some organization. But you could do it, and it's good for you. And then you get that. So you're doing that in 5-2. And the ones I assigned are doing like 4 or 6 rectangles. I mean, I didn't make you do infinite number of rectangles or 32 rectangles. I didn't. You know, so you can do a little bit of that. All right, hang on. Did you want to? So hang on. So in 5-3, they tell you that area under a curve. They tell you this. They tell you that if you have a function that goes from A to B, that the area under this curve is, they finally tell you that it's actually an integral. From A to B, f of x dx.
Okay.
In 5-3, they start telling you
That's what you use.
that integrals are area. In 5-2, they didn't really give you that yet. They're still all about the summation symbol. They don't make the connection for you yet in 5-2. So you're adding up rectangles in 5-2. In 5-3, they tell you, hey man, an integral is actually area under a curve. And so you're looking at this, but they still don't tell you how to do it. Let me say something. Until 5-4. In 5-4, they tell you how to do one of these integrals. Now, I just told you how to do one. The way you do one of these integrals is you find the antiderivative of f of x, which we called capital F of x yesterday. Do you remember that? You do his antiderivative. You evaluate from a to b, which meant plug in the b, f of b minus f of a. You hear me? Telling you how to do this integral is now up in 5-4. So in a way, I took you on a long journey today. 5-2, 5-3, 5-4. I don't really expect you to go catch up to me this weekend, but you could start exploring. You could add up some damn rectangles in 5-2, but you also have to get good at 5-1, which has nothing to do with area, just antiderivatives. But you can add up some rectangles. You can start thinking about how it's area under a curve, and then this is how you do them. I mean, I taught you how to do it already. This last 5-4 here, this thing is called the fundamental theorem of calculus, right here, which is how do you do one of these definite integrals. It's called the fundamental theorem of calculus. All right, man, that was fun. I hope you liked it. Well, it's, yeah. Well, then, right. You know, you're lucky, you're right. You're lucky I'm here, because I'm making it easy for you, dude. I swear to God, you should go do my homework and you have to add up some rectangles. I'm making it easy for you. I don't make you do infinite number of rectangles. Some people do. But doing an infinite number of rectangles ends up being this. Yeah. So why the hell bother, right? But, you know, it turns out in real life, there's a lot of things you can't integrate. Like, could we integrate this? Yeah, 1/3 x cubed. It turns out in real life, there's some stuff you can't find an antiderivative for. And so then maybe resorting to adding up rectangles is your only way to do something. Maybe you can't do this. So this background information of adding up rectangles is important. It's vital. But you kind of slip past it and start integrating when you can. Yes?
Does it matter what interval? Like they gave us 0 to 2. Do you get?
So I picked 0 to 2, and I also picked that it was 4 rectangles. And then, by the way, the width of each rectangle is b minus a over n.
Okay.
That seems like it's some fancy formula, but what is it? It's the width of each rectangle, which was 2 minus 0, which was a width of 2 divided by how many rectangles? 4. A width of 2 divided by 4 rectangles. Each width is going to be a half. I mean, it's not really some fancy formula. It's very logical. Take that whole width and divide by how many rectangles you're going to use, and that's the width of each rectangle, right? What else? Anybody want to say anything? Ask me anything? Can I tell you this? I'm going to back up to 5-1 and say one thing, or a couple things here. You know, when we threw an object up in the air, it had a height equation. The height equation was usually called S of t, or position, and it was, if we were on Earth, and if we were in feet per second, then it was 16t squared, negative 16t squared, plus v naught t plus s naught. Right, you guys? Remember that? Throwing something up in the air. And then we learned that if we took his derivative, what do we get when we take his derivative? Yeah, we get velocity. I could call it v of t, but it's the derivative of him. Right. And go ahead and tell me, what is the derivative of him?
Negative 32t plus v sub 0.
Yeah, right, because that's a number times t. So when you take the derivative, you get that number. Oh, and the derivative of that number is 0. Right, okay. And then, if I took the second derivative of s, that's called acceleration. That's acceleration. These are major topics here, right? Position, velocity, and acceleration are related like this. And this is important in physics classes. Anyway, what is this derivative?
Negative 32.
Yeah, cool. And by the way, that's gravity. That's what our acceleration is when we're on Earth. It's that number is gravity in feet per second. All right, so you know that concept. All right, in this chapter, they revisit that concept in 5.1, but what they do is they act like they start with acceleration. Like, what if I was on Mars and the acceleration was negative 2.6 feet per second? So I'm saying I'm on Mars, and Mars has a lot less gravity. You follow me? So instead of negative 32, I'm saying I'm on Mars, and this is my gravity. So this time what I'm doing is I'm learning, instead of starting with height and taking the derivative to get velocity and another derivative to get acceleration, I'm starting with acceleration. How do I get velocity? Please tell me. Yeah, but how? What am I doing?
Integrating.
I'm integrating, or anti-differentiating, or integrating. Right. That's the big concept. It's just the same concept backwards. That if you have acceleration and you integrate, you get velocity. If you have velocity and you integrate, you get position, or height.
Right.
Let's just watch me do it. So if I want the velocity equation, I'm going to integrate this with respect to t. All right, how do you integrate a negative 2.6? It's a number. With respect to the variable t, you get?
Negative 2.63.
That's right. Okay, now I'm back in 5.1. There's no bounds on this. It's called an indefinite integral, and I should put plus c. You need the plus c, but this was a new idea. With this guy, you didn't need the plus c. You had to evaluate him. So this was a little bit ahead of us.
Okay.
But cool. It turns out the plus c turns out to be, well, yeah, because what I know is that at time equals 0, what is my velocity? And let's say I don't know, I could know a specific number, but I could just know a generic idea that at time 0, my velocity is this number. Watch what happens when you plug this in right here. If you plug this in, okay, what's going on? So the v is a v naught, yeah. The t is a 0, yeah. Okay, so what's c? C is v naught. So this plus c that was just a stupid arbitrary c in our previous problems from Monday, it has some meaning here. The plus c in a velocity type problem like this, the plus c is the initial velocity. So I'm going to replace that. My velocity equation now becomes negative 2.6t plus v naught. Looks a lot like this, right? With a different gravity. Right. Anyway, if you want position, how do you get position s? I guess you got to integrate this, don't you?
Right.
All right, okay, check this out. Watch this. Let's integrate with respect to t. Are you ready? Integrate with respect to t. This is Monday now, back to Monday. Integrate with t squared.
T squared
Divide by 2. T squared divide by 2.
Yeah.
So t squared, and when you divide by 2, it's negative 1.3. All right, now look. V naught is some number. When you integrate that number with respect to t,
So
V naught t.
V naught t. I mean, right, you can sort of cheat if you just look up there. But anyway, and then it's plus, we're done with the integration, and then it's plus some constant. And this is the height s.
Right.
But it turns out that that constant is
S of 0.
the initial height. Right, it turns out that constant is actually the initial height. So see how you can start with gravity or acceleration and derive these formulas by doing anti-derivatives. Start with acceleration, integrate to get velocity, integrate that to get position. And the plus c's are these v naughts and s naughts. Okay, cool. There's some real problems maybe we could work on, but we won't today. Listen, so you can work on some stuff. You have a nice long weekend. I'll see you next Monday. Where am I? 5-1, 5-2, 5-3, 5-4? I mean, sort of. You don't have to be there by Monday, but you can explore all you want.